Hi, in this video we are going to review some basic integration rules from Calculus 1 because you need these rules for Calculus 2. Now the first rule, we usually call this the constant rule, where you take the integral of a constant k, where k is any single value, and du. I use the letter u instead of x because we are now learning the u substitution from section 5.5. Now, for any integral of k du, any constant k, all you do is you multiply k by the variable x and add c. So that is the constant rule. And why did we get this value here? Now, if you take the derivative function of this one with respect to u, then you can see that you should get back k, which is the original function here. So let's take a look at some example here. So for example, I take the integral of number 10 dx. In this case now I just use the variable x instead of u, but we mean the same thing here. So the integral of 10 dx, 10 is a constant, therefore all you do is you multiply by 10 by the variable x and then add the constant c at the end. Now you can check this to make sure that this is correct. If you take the derivative function of this one, then 10x just become 10, and the constant when you take the derivative function of that, it just becomes 0. So all you get back now is 10, which is the original function here. So we know that this is the correct formula to use. So the constant rule is very simple. All you do is you take the constant, multiply by the variable that you are taking the integral with respect to, and then adding a constant c at the end. The second rule is, and it's very important, is the power rule. Now, if I take the integral of any variable and to the power of n, so n now can be anything, n can be any value, a single value, any constant, because n is a power of u, therefore we call this to be the power rule. And the rule is working this way. We keep the variable as the base, we add 1 to the exponent, and all the exponent we divide by that, and then we add c at the end. So make sure that n could be any number except -1, because what? Because when I have -1 for n, then -1 plus 1 give me 0, and we are dividing by 0. And you know that dividing by 0 is undefined in math, so it doesn't make sense. So n can be any power, any exponent except -1. We will get another different formula for the case of n to be -1 later on. Okay, so that is the power rule. So let's take a look at some example. Let's say this one. I take the integral of x to the 6 dx. This is the power rule we can apply here. X is the base, or x is the variable with respect to the x here, and the power here is the constant number 6. So all you do now is you add 1 to the exponent. So 6 plus 1, and take the whole quantity here, divide by that at the bottom, and then add c at the end. So 6 plus 1 give me 7. 6 plus 1 give me 7. So anything on the exponent must be down here. So we add 1 to the exponent, divide by the same amount of quantity that you get here. Make sure that n is any constant except -1. And this is the power function, then we can apply the power rule. Okay, let's try another example. How about this one? Now, the same thing, I still have the base as a variable x with respect to the x, and the exponent now is just a negative value. Before, I had +6, but now I have -2. Doesn't matter, as long as this number is not -1 that I mentioned here, then it should be fine. Now we can still apply the power rule. We add 1 to the exponent, -2 plus 1, and then take the whole thing, bring it down here, and divide by that. and add c at the end. Now we can simplify this further. -2 plus 1 give me -1. -2 plus 1 also give me -1, and add c at the end. We always plus the constant at the end for any indefinite interval. Now we must simplify this function. So the -1 at the bottom here, we can bring the minus to the outside of the fraction, and then the negative exponent, we can bring it down from the numerator to the denominator and changing the -1 to +1. So this is number 1 here. I don't have to write that. And then adding c. Okay. Remember that for any negative exponent, for any a to minus b, then it just becomes 1 over a, and we are switching the minus b to positive b by switching it down to take the reciprocal of that. Okay, the same thing here. So I bring down the x and then changing the -1 into +1 here, and we use this rule here. Okay, let's take a little bit more example. Now let's take a look at this example. We take the integral of square root of x plus x to the third power divided by x and then dx. Now, at first you may think that we cannot apply any of the rule that we just saw in the last two formulas. But before taking any integral, the first thing is we must simplify the function as much as we can so that we can see which formula we can use. Now, if I rewrite this one, I know that the two terms here, they are both dividing by x. So, well, I can just split the first one divided by x into here, and then keep the add sign, and then x3 divided by x at another term. We can split them, okay? The next thing, we have to simplify it. How do I simplify that? I know that the square root means the power of 1/2, and I keep the same x here, and then x3 divided by x, this is x to the first power. I know that we have the same base, so I keep the same base. I subtract the exponent. 3 minus 1 give me 2. Now, we already simplified the second term. How about the first term? I know that this is also the same base x. I bring it down here, and this is the power of 1/2. I don't write anything here. That means this is the power of 1. So the same base dividing, so we keep the base x, we take the exponent, we subtract them. So 1/2 subtract 1 is here, and then I keep the same term here. Now simplify this further. Okay, so minus 1/2 minus 1 give me minus 1/2. That's basic subtraction, right? And then x squared here, and then dx. Now we simplify the complicated function right here. Until now, we get something that we can see. We can apply the power rule, because this is just the power function of the two functions, which we can apply the power rule to each of them. Okay, so this is easy. The first one, I add 1 to minus 1/2, and then I divide the whole thing at the bottom. The second one, I add 1 to 2, which is 2 plus 1, and take the whole thing, divide by that, and then add c, which is the power rule we saw earlier. And now we can simplify that another step. Minus 1/2 plus 1 is just 1/2. Again, this is 1 minus 1/2 plus 1/2. 2 plus 1 is 3. This is also 3, and then c and c. Okay. Now dividing by a fraction means multiplying by the reciprocal of that. So dividing by 1/2 means I multiply by 2 over 1. Flip it upside down here, and we keep x to the 1/2, and then the same here, the same here. And then the last step is you just simplify one more time. Number 2 divided by 1 give me 2. X to the 1/2 power means that this is the square root of x, because 1/2 power means the square root of x, and x to the 3rd power over 3, and that's c. So this should be the simplified answers for this problem. Okay, let's take a look at more example on this rule. How about this one? Okay, we get something with x, but now I have some kind of radical. The index 3, the power 4. So how do I write this one as the power function? Well, we know that the index should go to the denominator of the fraction. The power should go to the numerator. So for any just go back to algebra. Any radical of a to the power b, it just does x to the power of the fraction. A, the index go to the bottom. B, the power, the exponent go on the top. The same thing here. X, we keep the base. The index 3 of the radical go down here, and 4, the exponent go on the top. So we just converting this radical into this exponent form, and if you get back to the exponent function or the power function, we can just apply the power rule. And if you do that, add 1 to the exponent and then divide by the whole quantity here to the bottom, and then add c at the end. That is a power rule. And the last step is 4 over 3 plus 1 is 7 over 3. The same thing here at the bottom. And dividing 7 over 3 means I'm flipping 3 over 7, and that's become the multiplication. And that is r, and plus c at the end. Okay, so that's a very good example for the power rule. Now let's take a look at another rule number 3. This rule is telling you that the integral of e to the u du is equal to e to the u plus c. So nothing is changing here. And why is that? Why is that the case? Remember, if I have e to the x function, and if I take the derivative function of that, or dy dx, remember any derivative function of e to the x, it's just e to the x, the same thing. So that's why e to the u plus c, if I take the derivative function of this one, it's just become e to the u, the constant becomes 0. That's why I get back here. So very simple formula. The integral of e to the u or e to the x is just e to the x or e to the u. Nothing is changing. And then we add c, which is a constant at the end, because its derivative is the same thing as the original function. That's why the integral should be the same thing as well. Okay, let's take a look at a quick example here. So let's say that I have the integral of phi e to the x dx. We know that any constant, we can just bring it to the front. Okay, and then all you do is we take care of the integral here. And we know that e to the x, when we take the integral, should be the same thing, and add c. So we do it here, we keep the phi in the front, and then the integral of e to the x, just e to the x, and then we add c at the end. Simple enough? Good. The next rule, the integral of u du over u equal to ln the absolute value of u plus c. Now remember before let's let me go back to the rule, the power rule. It's here. U to the n power, I said that n cannot be negative 1. Okay, let's say n is negative 1, then negative 1 plus 1 is 0, so you are dividing by 0. But u to the minus 1, for n to be minus 1, u to the minus 1, and you go back to this case, u to the minus 1, this is the negative exponent, So if I switching this to positive exponent, that is 1 over u to the first power, which I don't have to write that. And now we have the formula for 1 over du. That's why I told you the power rule. We cannot have a -1 for the exponent. And anytime that we get the exponent to be -1, then we have to use this formula. So any integral of 1 over u du is just becoming the ln or the natural log of the absolute value of u plus c. And we saw this from Calculus 1 class. This is just a quick review. Now let's just apply this formula here. Okay, let's say I have 1 over 5 x dx. We know that this is 1 over x, right? This is 1 over x part here. So all we do is we bring out the minus 1/5 to the outside of the integral, and we keep the 1 over x on the inside. And we know that the integral of 1 over x dx or 1 over u du is just ln of absolute value of u. In this case, we use the variable x, so it's just becoming 1/5 in the front, ln of the absolute value of x, and then add c. Yeah, the same thing except the variable u now is just x. The reason that I use in this context because I want you guys to be able to use to apply that to the use substitution from section 5.5. Okay, so that is the rule number 4. Now let's take a look at rule number 5. Okay, now we have the integral of a to the u du. Now this is the exponential function, and the reason we call this to be the exponential function because the base now is a single number a, and the variable now is in the place of the exponent. So this is the exponential function, and the rule for the iteration of this one is just 1 over ln the natural log of the base a, and then the same thing multiplied to here, and then add c, and make sure that the base a must be bigger than 0. Okay, let's take a look at this example for the rule. Let's say I have some integral of 10 multiplied by 2 to the x power dx. We know that this is the exponential function because the exponent now is not a number, but this is the variable. Okay, again, number 10 is just a constant. I can bring it outside of the integral. The inside now is just 2 to the x dx. This is the exponential function. We must apply the exponential rule here. So that's become what? The 10 stay the same. It's outside. The base 2 now is just a, right? So 1 over ln a, the base, so 1 over ln of 2. And then multiply by a to the u, the whole quantity here. So 2 to the x, go down here. And then adding c at the end. Okay, that's still simple. Okay, let's try more rule. Rule number 6. The integral of psi of u du is minus cos psi of u plus c. We know that because when we take the derivative of cos psi, it gives me minus psi. And minus psi with the minus in here give me plus psi. That's why I get back here. So the integral of psi of u du is minus cos psi u plus c. Example. The integral of psi of x divided by minus 2 dx equal. I know that the minus 2 here, which is another constant, I just bring it outside. So minus 1/2, keep it outside. And then the basic formula for the integral of psi of x dx is just minus psi of x, cos psi of x plus c. So all we do now, we keep the minus 1/2 in the front. The integral of psi of x dx is now just minus cos psi of x from the formula. and then add c. And the last step is to simplify the answer. Minus and minus, when we multiply them, it's become plus 1/2, and then cosine of x, and then plus c. So always simplify the answer at the end. Okay, let's take a look at more example. Also more rules. Now, the integral of cosine is psi, and that's c. Why? Because when I take the derivative of psi, I get back to cosine. Okay, so that's all. Example. The integral of 11 cosine of x plus x and dx. Now this is the addition, so we can just split the two terms individually and then take the integral for each of them separately. Okay, easy? Okay, that's easy. Cosine, when I take the integral of cosine, that becomes psi. So cosine becomes psi of x dx. 11 is just a constant, it stays outside. X, this is the power function to the power of 1, right? So using the power rule, 1 plus 1, and then dividing by the whole quantity, 1 plus 1 and plus c. And don't forget to simplify the expression. 1 and 1 give me 2, and then 2 down here as c, and then the same 11 psi of x. Okay, so let's go some more rule here. The rule number 8, the next one is the integral of the tangent. Tangent is sine over cosine, the ratio of sine and cosine. So the integral of tangent of u du, we saw that from calculus 1, is equal to minus the ln or the natural log of the absolute value of cosine of u and plus c. Let's try one example on that here. Let's try to find the integral of sine of x plus 3 tangent of x dx. Now again, we can split them because this is just the addition. So the integral of sine of x and then dx plus 3 tangent of x dx. 3 is constant, so I can bring it outside. Doesn't matter, right? We did that many times in this videos. Now, the sine of x, when I take the integral, I should get minus cosine, because that is from the rule we saw earlier for the integral of psi. That should be minus cosine from here, right? Psi minus cosine. So go back here, psi minus cosine. 3, keep that in the front. Tangent, go back to the rule for tangent, is minus ln of cosine, the absolute of cosine. So minus ln, the absolute value of cosine of the variable x, and then add c. And then simplify this one. Minus cosine, minus, because this is minus, so minus and 3 give me minus 3 ln of the absolute value of cosine of x and plus c. And this is the simplified version of the answer that we can do. Okay, we have a few more rules for the basic formula that we all should know. The next one is rule number 9. The integral of cotangent of u du is ln psi of u inside the absolute value plus c. And then the next one is secant of u du is ln of the absolute value or the natural log of the absolute value of secant u plus tangent u plus c. And the next one is the integral of cosecant u du is equal to minus of the natural logs of the absolute value of cosecant u plus cotangent u, and then add c. Well, these three rules we'll see more example in the next videos. But for now, let's take a look at the final rule, and this is very important popular, and you see that in a lot of the homework assignments. The integral of du a square plus u square. Now we assume that a is bigger than 0. And that is equal to 1 over a arctangent, inverse tangent, right? U over a plus c. This is a very important rule. So make sure that you can see that the variable u had a square term, and then the number, make sure that this is a perfect square so that we can rewrite that as something to the power of 2, and that equal to 1 over that perfect square number a, and then add arctangent, and then the ratio of u and a, and then add c. Let's take a look at one example to make more sense on this problem. So imagine that dx, we take the integral of dx, 9 plus x squared dx. Now anytime we see that there are two terms in the denominator and one term is the square, we should check that this is the adjacent side, right? Adjacent square, the square term. The next one is the last, the number must be a perfect square. We know that 9 is the perfect square of 3, because 3 squared give me 9. So this is a perfect candidate to apply the arctangent formula, right? So this is a squared, a is 3, x squared, and then dx on the top. It's just become that 1 over a, or 1 over a is 3, so 1 over 3, arctangent is here. The ratio between the variable and a, the variable now is x, a is 3, so arctangent of x over 3, and then add what? Add c at the end. And there's nothing we can simplify here, so this is the final answers. So in this video we saw that there's about 12 basic formula that we should know in order for you to learn and understand the use substitution rules from section 5.5. The first one is the constant rule, the power rule, the exponential rule, and then the 1 over du, 1 over u, or the natural log rule, exponential rule for any base a, sine and cosine, tangent, cotangent, and secant, cosecant, and the last one is arctangent. So we make sure that in the bottom there's u square, there's a square term, and there's perfect square. Then we can apply the arctangent rule. Okay, so that is the some basic formula for integrations to make sure that you guys get a good review so that we can move on to calculus 2. Thanks for watching.